So here we're going to look at an example that we're going to come back to throughout the rest of the semester, because I think it's a good example. In number 1, it says the death rate from heart disease and death per 100,000 people is modeled by R of t. Then the U.S. population in hundreds of thousands of people is given by P of t. And let t be the year since 1960. So in each of those equations, when you plug a value in for t, so if you put t equals 5 in, that means you're going to be 5 years since 1960 in each of them. Notice that they are both linear equations, like y equals mx plus b for each of these. And in part A, what we're going to do, write an equation for the product r of t times p of t. We're going to call that product d of t, so we're going to call it a different function name, and then explain what that equation represents. So if you multiply those two functions together, you're going to take the r of t function times the p of t function. And I already have it worked out because of the writing involved. So multiply the two together. And this is just an amped up example of multiplying 2x plus 3 times 5x plus 7. So you want to distribute to each of the parentheses. And you get a really big mess, but that's okay. You don't get very nice numbers with this. And the simplified version is right here. Okay, so take a minute and do that and make sure that you get the same answer I do. It's just, again, it's just a really amped up example of multiplying two binomials that we did earlier. You just don't get nice numbers here. Okay, so then the question is, explain what this equation represents. So if we look at what we actually multiplied together, here we multiplied the death rate, which was the number of deaths per 100,000 people. So we took number of deaths per 100,000 people, and we multiplied that by hundreds of thousands of people. Now remember, we can treat that as like over 1 because there's nothing in the denominator. So what happens here is the hundred of thousands people cancels out. So what you're left with is just a cheery example of the number of deaths. So what this equation represents after we multiplied the death rate by the population, we end up with the number of deaths. So d of t is the number of deaths, and technically due to heart disease. Okay, so that's how looking at the units can help you interpret what the equation represents. Okay, so then in the next part, I give you a table. So basically using this function for d of t, putting in a whole bunch of values for the year since 1960. I leave a couple of them blank at 10 and 40 for you to substitute in yourself, just to plug the numbers into this equation to make sure that you match up with what I get, just to give you practice for evaluating a crazy looking function like that. Okay, and then what I want you to do is on the scatter plot, make a scatter plot given this grid. Okay, so the year since 1960, remember that's time, so that's going to go across the bottom. So you got to figure out a nice scale for that, and that's fairly straightforward. And then the number of deaths should go up the side. Okay, so if you look at, after you evaluate when t is 10 and when t is 40, create a scale going up the side. Now that's something that you should be able to do at this point in the class. So I'm going to go ahead and put my answer up there because it takes a bit of time to do. So pause the video and I'll put the answer up for what I have for the scatter plot. Okay, so that's what I have for the scatter plot. And across the bottom is the number of years since 1960, and then up the side is the number of deaths. And again, due to heart disease. Now yours may be a little bit different depending on how you made your scale and how you plotted your points, because you have to guess where they are, because you're not going to know exactly where 886,200 is. So you have to do a little bit of estimating here. I just used 50,000 for each tick mark, and that gives you a pretty good graph. That's probably the best one to use. Not to brag or anything, but that was pretty good. Okay, so after you plot the points, what you might notice is, if you look at the shape of what's happening here, notice there's kind of a curvature to the graph. Okay, if you kind of follow the points along. So in evaluating D of 10, excuse me, evaluating D of 10, you get 898,128, which tells you the number of deaths to predict in 1970. So if we kind of follow that shape along, it kind of looks like an upside down, or part of an upside down U shape. Okay, so if I kind of follow them along, they look something like this. So notice that's kind of a little over half of an upside down U shape. So we notice that up in here, there's a maximum number. Okay, so if I asked you what would you predict the maximum number of deaths to be, you would say somewhere in here. Okay, so if we, on our grid, kind of created that shape. Now, if it was perfect, it would go through the points because we actually used an equation to plot the points. Now, I missed mine just a little bit there. But because we used an exact equation to plot the points, we should be having a graph that goes through the points. Okay, so at D of 10, so when you trace 10, okay, we're way up here at just under 900,000. In the last question, part D, it says estimate when D of T is 500,000. Well, 500,000 is here. And then when you go over and hit the graph, notice that we're just past this tick mark here. So if you go straight down, we're just past 50. So you would estimate maybe at about T equals 52, which represents the year 2012, because you add 52 to 1960. So in 2012, you would predict about 500,000 deaths due to heart disease. So that's a good example, because I think it's a really good example of showing how the units work and then actually have meaning to when you multiply two functions together, you end up with an equation that's meaningful, the number of deaths.